until we're on time. We won't start until the official time because I don't have anything to review tonight, but I want to get at least a share screen going. I'm also trying a different lighting scheme. I hope it works better. It's kind of getting light on my face instead of in the background. See if you like it better. Let's see here. All right, let's see if this will work. All right, let's enlarge this a little bit. Let's lock it into place. I hope that's good enough. So I have a blank screen tonight because there's nothing to review. That is, unless you have some questions. So are there any questions about the previous lectures and material before we get started with the real stuff, the new stuff tonight? Everything's ultimately transparent and clear. I know I'm exaggerating. Radha, your last name, Mastandrea, it looks Italian, but your first name looks like Indian. Is that right?
Yeah, I'm half of each.
Oh, so you are. Oh, that's very interesting. Oh, that's really very interesting. You know, I spent quite a while in Italy working with some collaborators there, and it's interesting to see how Italy is changing over time.
Yeah, a lot of my Indian friends actually think it's from the Mastandrea is from India, and they get very confused when I say no, it's actually Italian.
So, did you grow up in Italy?
Oh no, I grew up in the U.S.
In the U.S., I see. Have you spent time there?
Not significant time.
Okay.
It's probably a few generations removed, I think, is a better.
Oh, okay.
I see. Yeah.
Okay. Okay, I'm going to get started then because it's about time. The first topic tonight, main topic, concerns the coupling of state spaces that correspond to different subsets of degrees of freedom of a given system. It frequently happens in physical systems that there are subsets of degrees of freedom that are physically distinct. For example, a two-particle system has degrees of freedom associated with one particle and then another set associated with the other particle. These different degrees of freedom might be dynamically coupled strongly in some circumstances and not coupled at all in others. For example, you could have two particles in orbit around one another, or you might have them separated, one here and one in San Francisco. Those are dynamical considerations, and those are also affected, of course, by the Hamiltonian, which could change depending on external fields and things of that sort. But the question I want to address initially is not dynamical questions, but merely one of the setup of the framework of quantum mechanics. Namely, what about the state spaces? So if you have a state space for one set of degrees of freedom and a state space for the other, how do you construct the state space for the compound system in which the particles may or may not be coupled together? So to take a specific example of this, let's suppose indeed we have two particle system. Let's call E1 the state space for particle 1. This is a set of wave functions, assuming this is a spinless particle moving in 3 dimensions. The state space can be identified with a set of wave functions. Let's call them phi of r like this. And for particle 2, this is identified with a different set of wave functions. Let's call them chi of r, describing particle 2. Okay. Now then, let's let E be the state space for the combined system, the two-particle system. Well, I think you know what the set of wave functions is in that case. It's wave functions I'll call psi that depend on the coordinates of both the particles. I will assume that these two particles here are distinguishable just to simplify the discussion like that. Okay. Now, a two-particle wave function like psi of R1 and R2 might be equal to a product of single particle wave functions, some phi of R1 times the chi of R2 like this. But what I want to emphasize is that this is not a general form for a two-particle wave function. Product wave functions like this are very common in homework problems, the quantum mechanics literature, hand waving arguments, all kinds, all over the place. People want to talk about product wave functions like this, but these are definitely not general. On the other hand, it turns out that an arbitrary two-particle wave function can be represented as a linear combination of products of single particle wave functions. To show you how that works, let's introduce a basis in the space E1. Let's just say this is a collection of wave functions. Let's call them U sub n of R. So you can think of that as an orthonormal basis. And likewise, a basis in E2, let's call it V sub m of R. That's the basis for the second particle. Then it's possible to expand the R1 and R2 dependence of an arbitrary psi in these two bases. And if you do, you can write psi of R1 comma R2 is equal to a sum on two indices n and m of some coefficients n and m of some coefficients c and m times un of R1 times a v sub m of R2, like this. And what this example shows is that an arbitrary vector or state vector in the state space for the combined system can be represented as a linear combination of products of basis states from the two constituent systems, like this. Now, when we have a situation like this, we use certain notation. We say that the total state space E is the tensor product of the two constituent spaces. We use this symbol, an X with a circle in it, to indicate the tensor product. And roughly speaking, when you see this designation like this, if you're in a math department, you need to learn a rigorous definition. But for our purposes in this course, it will be sufficient if you think what E1 tensor product E2, what it means is it means the set of all possible two-particle wave functions or wave functions that can be created by multiplying together wave functions from the two constituent spaces and forming linear combinations like this. Okay, it's certainly not restricted to this simple product form. All right. Now then, in addition to taking tensor products of spaces, we can take tensor products of wave functions, i.e. state vectors. So for example, in this product of wave functions here, if we write this in Ket language, let me draw a line here to separate this off. Writing in Ket language, you could write Ket psi, which is a state vector in the product space E, is the tensor product of a Ket phi in E1 with a Ket chi in E2, like this. In other words, a tensor product of state vectors corresponds to just multiplying the corresponding wave functions together. And partly for that reason, in the physics literature, one normally omits the tensor product sign when, let me do it right, when multiplying such wave functions from the two constituent spaces. You just write it as Ket phi times Ket psi, excuse me, Ket phi times Ket chi to give you Ket psi. But what this means in wave function language is a multiplication of the wave functions. Likewise, taking these basis states in the two different spaces, we can associate the UN with a Ket U sub n like this, and the wave function Vm with a Ket V sub m like so. And we can talk about forming the tensor product of those U sub m tensor product with V sub m like this. And let's just make that an abbreviation. Let's just call it NM like so. And if we do, then this expansion here can be written this way, is to say that psi is equal to a sum on n and m of coefficients Cn Cm times nm like so. This is a way of saying, or a way of illustrating the fact that in the tensor product space, a basis in the tensor product space is given by forming the tensor products of all combinations of all possible basis vectors from the two constituent spaces. So I hope this gives you the basic idea of some of the mathematics and notation which is used in forming tensor products of spaces. And as I say, physically, this corresponds to combining the state spaces for subsets of degrees of freedom that go together to form a larger system with a larger number of degrees of freedom, illustrated here in the case of two particles. Another example to think about is where we only have one particle, but we consider one state space that involves only the orbital degrees of freedom. That state space can be thought of as the span of the basis states. Let me write them as R. The basis position eigenkets are like this. But then we also have, if the particle has spin, we also have a spin state space, which can be thought of as the span of the state vectors. Let me write them as S comma M sub S, like, or better yet, let me just write them as SM. I'll omit the subscript on the S like this. This gives us a state space that we're familiar with in dealing with spin systems. We just went through some lectures on the evolution of spins in magnetic fields, and this was the state space that we used for those problems. All right, so if we talk about the total space then being the tensor product of orbital times spin, and this would be useful if we want to talk about the combined dynamics of orbital and spin. We're not demanding that they necessarily be dynamically coupled. They usually are, but if they aren't, it doesn't matter. This is still the state space. But when they are dynamically coupled, you need to talk about the evolution in the total space and not in the two constituent spaces. That doesn't make any sense if they're dynamically coupled. In any case, a basis for E total then would just be the product of the bases from these two different constituent spaces. So in other words, you take a state vector R, basis state in E orbital, form the tensor product with SM for a basis state in the spin space. By the way, the S is just a constant here. It's just characteristic of the particle. So if it's understood, you can suppress it in the notation. Allow me to do that and just define this to be RM like this. This just defines this ket like so. It then follows that an arbitrary state in the combined space E total is a linear combination of those basis kets. And we can write it this way: if I have some state psi, which is contained in the total space, then psi as a state vector is equal to what? It can be equal to a sum like this. Well, excuse me. Before I proceed, let me make a point I forgot to make, which is that in this product of basis vectors, the index R is of course continuous. It runs over all three-dimensional space, whereas the M index, which is the only variable here, is a discrete index. So anyway, keep that in mind. One of these indices is continuous and the other is discrete. And so what that means is that psi can be represented as an integral over the continuous ones, d cubed R, and a sum over the discrete ones, M like this, of R and M, the basis states, times the expansion coefficients. And the expansion coefficients are what we call the wave function. So we can write that as psi of R comma M. You can invert this by writing the wave function psi of R comma M is equal to the scalar product of the basis state Rm with the state vector, abstract state vector psi. Wave functions in general are nothing but the expansion coefficients of the abstract state vector with respect to some definite basis. And that's just what we're doing here, except here that now we've got the continuous index and a discrete one. But I'm writing it this way as psi of R comma M because both these indices play the same role. They just give us the variables upon which the wave function depends. All right.
Excuse me, I have a minor notation question for what you just.
Yes.
You wrote psi as a function of R and M. Why did you do that instead of just saying psi sub M?
I'm going to explain that in a minute, but I'm going to address that question in a minute. But the reason is, I'll answer the question now. The reason is that both the R and the M play the same role. Is that the wave function in any context whatsoever, a wave function of any type is nothing but the expansion coefficients of the state vector with respect to some basis. So the wave function is labeled by the same indices as the basis vectors are. And these basis vectors have one continuous index R and one discrete index, where is it here? And one discrete index M, and psi depends on both of them. Okay. So I write it this way in order to emphasize that the R and the M play the same role here. Is that clear?
Yeah, no, that makes sense.
This is actually an interesting point, and if you want to think about this, read the notes, because in the notes I go into it in more detail than I'm able to in lecture. And I think I made some effort in the notes to explain it more carefully.
Okay, thank you.
All right. Now then, now to readdress that same question that was just raised, you might prefer a notation in which you write psi sub M of R And it's all right with me if you do that, as long as you recognize that both these indices, both these variables really play the same role. But if you want to write it that way, another way of thinking about the wave function then for a particle of spin is to arrange the different m values in a column and to write psi of r then in this way without an m index, where it's understood that we're not talking about a scalar wave function, but rather a multi-component object that has psi sub s of r in its upper component, and it goes dot, dot, dot down to psi sub minus s of r. I'm hoping this is not too, I'm writing this perhaps too small, but I'm hoping you can understand that. This is what you call a spinor, or more exactly a spinor field, because it's a spinor is a multi-component object that's indexed by the magnetic quantum number. But in this case, the components are also functions of position. So that makes it a spinor field on configuration space. So if you prefer to think about it as psi of r comma m, or psi sub m of r, or just simply psi, which is understood to be a multi-component object, I won't argue with it, any of that. That's all. Those are all valid ways of thinking about it. But what I do want to say is that the r and the m play a similar role in this description. So particles with spin then are described by the wave functions for them can be thought of as spinor fields or psi of r comma m, whichever you want. All right, so that's the case of spin. Now I've illustrated so far the tensor product of state spaces and also the tensor product of vectors in those spaces, which just means multiplication of wave functions. One can also talk about the tensor product of operators. Let's say I've got an operator A1 that acts on the one space E1 and another operator A2 that acts on the space E2. So in the case of orbital and spin, A1 for the orbital space might be the position operator, and A2 for the spin space might be S of Y or something like that. All right. Now then, we can define an operator I call A1 tensor product with A2. And this is defined by its action on basis vectors. Again, let's let a basis in E1 be what I'll call the u sub n basis, like this. Oh, let me write it in Ket language here. It's a collection of Kets u sub n. And the basis in the other space, let's write it as a set of Kets v sub m, like so. So A sub 1 tensor product with A sub 2 is defined by its action on the basis cats, as to say the tensor product of the basis cats from the two constituent spaces. That should be an n here, u sub n times v sub m. And it's given by letting the A1 part act on the u part. And then you form the tensor product of that with the A2 part acting on the VM part, like so. So this defines the action of the tensor product operator on a set of basis states in the tensor product space. Now, by linearity, an arbitrary vector in the tensor product space is a linear combination of such basis states. And so you just extend this formula by linearity. One can show that if you do that, the answer is actually independent of the choice of the basis. So this then becomes the definition of the tensor product of operators. There are certain operators that occur rather frequently. One of them is where you've got A1 for the first space multiplied by the identity in the second space. And if I allow this to act on a tensor product of, let's say, a phi times a chi, then what it does is the A1 acts on the phi part, and the 1 doesn't do anything to the chi part. So this is an operator which in effect acts only on the first space and not on the second. Similarly, you can have one tensor product with A2 acting on the same thing, and what it'll give us is a phi for the first part, tensor product with A2 acting on chi. And I hope that's clear. Anyway, operators of this form are quite common when we have operators, some operators act in effect only on the first space, other operators act only in the second space. If we're talking about the two particle system, you might have the position of particle 1 and the position of particle 2 would be examples of such operators. Now, when you have such operators, an important fact is that they commute with one another, that A1 tensor product with 1 commutes with all operators of the form 1 tensor product with 2. And the reason is because the A1 and A2 in effect act on different spaces. Now, in the physics literature and in textbooks and almost everywhere, A1 tensor product with 1 would just simply be called A1. And likewise, 1 tensor product with A2 would just be called A2. This is a slight abusive notation because it's confusing an operator that acts on space E1 with an operator that acts on space E. But if you're willing to gloss over that, you can use this notation, and that's more or less what we'll do in this course. All right, but such operators, as I say, commute with one another. So this is the notion of the tensor product of operators. All right, now to go back to the question of particles with spin and their wave functions, let's talk about Hamiltonians for particles with spin. We wrote down the Hamiltonian for a particle, spinless particle moving in a given electromagnetic field. I'll remind you that it's kinetic plus potential energy, in which the kinetic energy is written in this peculiar form, P minus Q over Ca, which is a function of position and time. In general, it's a function of position and time, plus Q times the scalar potential, which is also a function of position and time, like so. So this was the Hamiltonian we discussed earlier for particles in electromagnetic fields. And this Hamiltonian, the origin of this Hamiltonian was that it was just borrowed from classical mechanics. On the other hand, spin is not a classical phenomenon. It's a quantum phenomenon, not suspected at the classical level before quantum mechanics, not much anyway. And so naturally, it doesn't appear in this Hamiltonian. Earlier, when we were talking about systems in which only the spin were the interesting degrees of freedom, that was the evolution of spin in time-dependent magnetic fields, where we talked about magnetic resonance and things of the sort. We used a Hamiltonian, which was given by minus mu dot B. And this is the Hamiltonian for problems of that sort, for when you have only spin degrees of freedom. What happens if we have both spin and spatial degrees of freedom? What do we do? Well, the logic of the minus mu dot B is that classically speaking, that's the energy of orientation of a dipole in an external magnetic field. Magnetic field here is allowed to be a function of both position and time in setting up that Hamiltonian. And so it's an energy, in other words. And so it's logical that that if we want to include the effects of spin, in the original Hamiltonian, what we ought to do is just simply add this term. So let me put it out here as minus mu dot B like this. Actually, you can see the necessity of such a term, because if we didn't have it and we just went back to our original Hamiltonian, if we took the case of a neutral particle where Q is equal to 0, well, the Hamiltonian, the A term and the phi term would both go out, and the Hamiltonian would just turn into a free particle Hamiltonian. But we know that for a neutral spinning particle, so like a silver atom or a neutron, we know this can't be the actual Hamiltonian, because of the fact that those particles are bent in inhomogeneous magnetic fields. That's what was shown in the Stern-Gerlach experiment. And so, in fact, what you need to do for such neutral particles is to add this minus mu dot B term, like that. And this then couples together both the spin and the spatial degrees of freedom. And one can show that this Hamiltonian actually describes the splitting of the beams, which is observed in Stern-Gerlach type apparatuses in which you have neutral spinning particles. The more complicated Hamiltonian above is required if the particle also has charge. This more complicated Hamiltonian is called the Pauli Hamiltonian, and the version of the Schrodinger equation that comes from using that in the Schrodinger equation is called the Pauli equation. It is basically a version of the classical Hamiltonian with this extra term grafted onto it. It's a somewhat ad hoc procedure that I'm describing here to come up with this Pauli Hamiltonian. And Pauli, by the way, was very aware that this was entirely ad hoc. And for that reason, he was reluctant to publish it when he first was considering this equation, because he didn't think he had a deep enough understanding of what it meant, which was true, he didn't. But fortunately, he did publish it, because it turns out it's a very valuable equation. And it's also basically correct. We'll understand this from a deeper standpoint when we get to next semester to relativistic quantum mechanics. Nevertheless, it's important to understand that when using the Pauli equation, the wave function is a multi-component spinner, such as I sketched out up above here. It has 2s plus 1 components for spin s. By the way, for an electron, which is spin a half, that means there are 2 components. And it's worthwhile remembering that the electron wave function actually has 2 components that you can think of as a 2-component spinner. You can call them psi plus and psi minus of R, where the plus and the minus refer to plus and minus 1/2. That's the m number upon which the wave function depends, just as it depends on the position variable r like this. Electron wave functions are two-component wave functions. You have to get used to it. It's because it's the way it is. All right. So that's a bit about the Pauli equation and Hamiltonians for particles with spin. The next topic I'd like to address has to do with what's sometimes called the addition of angular momenta. And I can explain this in rather general terms. It goes like this. Again, let's say we have two state spaces E1 and E2 like this, and we're going to take the tensor product of them to construct a compound or total space. I'll call it E like this. Each of these constituent spaces, E1 and E2, in essentially all physical examples you can think of. Maybe before I go into that, let me just mention a few more examples of where we couple together state spaces of different degrees of freedom. I mentioned already how we construct the state space for a two-particle system out of two copies of one particle systems. That's one example. Another one is combining orbital and spin degrees of freedom for a single particle into the total Ket space for a single particle that includes both those classes of degrees of freedom. Another example is where we couple, for example, the dynamics of an atom to the atomic nucleus. Nucleus is a spinning particle that has a magnetic moment. And when we combine them together, what we get is an enlarged system where E1 refers to the atom and E2 refers to the nucleus. We'll actually do this when we study hyperfine effects, if we get that far this semester, which I hope we do. Anyway, that's an example. Another example is where we have an atom coupled to the electromagnetic field. That's where E1 represents the atom and E2 is the field. In some approximations, that the coupling between the two can be neglected, and we can talk about just the evolution of the atomic system alone. But if we do that, we miss out on certain phenomena which are connected to the coupling between those degrees of freedom, such as the emission and absorption of radiation. So to deal with the latter problem, one has to couple together the state spaces for these two dynamical subsystems, the atom alone and the entire electromagnetic field, which is a big dynamical system. So that's yet another example. There's actually quite a few examples of this, which we'll see in the course. And in all cases, each of these subsystems has its own state space, and the total state space is the tensor product of the two. All right. Now, in all these examples, and in fact, in all examples, physical examples that I can think of, each of these spaces, E1 and E2, has rotation operators defined on it. That's to say, there's a definition of, let's call it U1 of n hat comma theta in axis angle form, and therefore a corresponding angular momentum operator J1, which is the generators of that. And likewise, there's an U2, which can be written in axis angle form, which acts on E2 and corresponding generators of that, J2. Each of these operators, each of these generators, J1 and J2, by themselves satisfy the angular momentum commutation relations. That's understood because that's what happens on any state space. Now, it turns out with the definition of U1 and U2, we can make a definition of rotation operators acting on E. Let's just call it U without any one or two subscript. U is just defined this way. It's U1 of the same axis and angle, tensor product with U2 of the same axis and angle. It's a logical definition for a rotation operator in the product space. That means that U, let me suppress the n and theta just to save writing. That means that U acting on a tensor product state such as phi times chi, like so, is just U1 acting on phi, tensor product with U2 acting on chi. That's the definition of a tensor product of operators, if you'll recall. You fill it in like that. You just rotate each of them separately by their own rotation operator. So let's make that definition. And let's abuse notation as people frequently do in physics and drop the cross sign here. So this means then that U is equal to U of n, let me write it out explicitly. It means U of n hat comma theta is equal to U1 of n hat comma theta times U2 of n hat comma theta, omitting the tensor product sign. But these can be written in exponential form. U1 is e to the minus I theta times n hat dotted into J1. And I'll set h bar equals 1 here for most of this discussion because it saves writing. And then U2 is e to the minus I theta times n hat dotted into J2. The axes and angles are all the same, but the J's are different for these two operators. Now, J1 and J2 commute with one another because they act on different spaces. So we can combine these exponentials as if they're ordinary C numbers. We get e to the minus I theta times n hat dotted into J1 plus J2. And that shows that this resulting operator, which is U for the entire space, is just what you expect for a rotation operator if we define J, the angular momentum for the product space, to be equal to the sum J1 plus J2. And
Sorry,
so
what does it mean when you're adding operators from two different spaces?
it's J1 cross 1, tensor product with 1,
Okay, there you go. Yeah, okay, great.
plus 1 cross J2. And nobody in the physics literature ever writes it that way because to them it's obvious that it's just J1 and J2, but that's really what it is.
Very good.
So in our space E, we've got a U of n hat comma theta and a vector J, which is the sum of the J's of the constituent spaces. Okay. So that takes care of the definition of rotation operators and the angular momentum in the constituent spaces. Now, in addition to that, one of the things we know is that the existence of rotations and angular momentum implies a standard angular momentum basis. So that E1 has got a standard angular momentum basis I can call gamma 1 J1 M1. Let me try to draw a line here to separate off what's below from what's above. And then this space has got a standard angular momentum basis gamma 2 J2 and M2. And in case you've forgotten, what this means is that, for example, looking at the U1, this is a set of basis vectors which are eigenstates of J1 squared and J1Z with quantum numbers J1 and M1. But if those two operators taken together do not form a complete set, then we introduce a new index gamma. And what that does is that inside the simultaneous eigenspaces of J1 squared and J1Z, gamma just labels the vectors of an orthonormal frame in that space and thereby resolving the degeneracy. That's all the gamma means. But anyway, in general, gamma is needed and we have them for both of these spaces. So this is the standard angular momentum basis. But as we've just learned, the product space also has rotation operators and an angular momentum. So over here, there ought to be a standard angular momentum basis gamma Jm, like so. All right. Now, taking products of the standard angular momentum bases of the two constituent spaces, tensor products really, gives us, as I just explained, a basis in the product space in E. But that's not the same as the standard angular momentum basis over here. So E now has two bases in it, one which is products of the basis vectors from the constituent spaces, and one's its own native a standard angular momentum basis, which is eigenstates of its own J squared and JZ. And the question now is, what's the relationship among those? Example of this comes from combining orbital and spin degrees of freedom. If the first one is E orbital can be thought of as the span. If I write its basis states, the standard angular momentum basis here has quantum numbers n, l, and m, where n labels an arbitrary radial wave function, Rn of r, indexed by n, and then the L and m is YLMs of theta and phi, like so. And the E spin is the span of let me just write it as SSM, like so. Better close this up like that. There's two m's here, so let's call it m sub L for the orbital part and m sub S for the spin part. But in any case, these are the two spaces. Now I want to draw your attention to what I've been calling irreducible invariant subspaces. Because I think this might be confusing, I want to explain it yet again. An invariant space means that you've got a subspace of the state space or the Hilbert space, which is mapped into itself by means of rotations. An invariant irreducible space is such an invariant space that doesn't have any smaller invariant spaces. In other words, it can't be broken down into any smaller ones. The way we get these invariant irreducible spaces is that we take the standard angular momentum basis and we fix all the quantum numbers except for the magnetic one. So for example, if I have the span, let's take the orbital part. If I take the span of NLM, where n and L are fixed, but the m runs from minus L up to plus L, that's the variable part. This creates a 2L plus 1 dimensional space, because that's the number of m values, which is in fact what I'm calling an invariant irreducible subspace. We can call it E sub NL because it's indexed by those fixed quantum numbers. As far as the spin goes, it consists of just a single irreducible subspace under rotations because S is a constant and just M sub S varies from minus L at the plus L. Now these spaces are invariant under rotations because if I take, using a general notation, gamma JM, and I apply a rotation operator to it, what I get is a sum on M values, M prime, let's call it, gamma J M prime, the D matrices DJ M prime M, which is parameterized by the rotation U. In other words, we get linear, when you rotate a gamma JM, what we get is linear combinations of other gamma JMs with the same values of gamma J, but only the M values are different. So in other words, this gives us, letting M run from minus J to plus J gives us a 2J plus 1 dimensional subspace of the Hilbert space, which is invariant under rotations. And they play a significant role in the theory of rotations. For example, as we'll see later on, the Hamiltonian operator is a multiple of the identity on these spaces. At least that's true if the Hamiltonian is for an isolated system and therefore rotationally invariant. Anyway, we'll get back to Hamiltonians later on. Let's just right now I'm just trying to draw attention to the importance of the invariant irreducible spaces. In this orbital and spin example, the spin part of it is a single irreducible subspace, but the orbital part consists of a whole bunch of them because of different N and L values. When we form E orbital with E spin, in this process of trying to compute the standard angular momentum basis in the product space, it turns out that we can take the irreducible subspaces one at a time. In other words, we can fix the value of N, we can restrict E orbital, if you like, to just one of its invariant irreducible subspaces by fixing the values of N and L. And then what we get is just a single irreducible subspace for the orbital part, and the spin is already the same. And we can look at the construction of the standard angular momentum basis from the tensor product of those two subspaces alone. And then later on, just basically form all possible combinations of N and L subspaces with a spin space to get the total decomposition. In a more general notation, we're going back to the gamma 1 J1 M1 and the gamma 2 J2 M2, which are the standard bases in the two constituent spaces, gamma 2 J2 M2, like so. Let's fix the value of gamma 1 and J1 and gamma 2 and J2. And in fact, notationally, let me just throw away the gamma 1 because it's going to be constant for this argument, and just talk about J1 M1 for a single irreducible subspace here, and then J2 M2 for a single irreducible subspace in the other space. If I do, then the dimensions of these two spaces are 2J1 plus 1 and 2J2 plus 1. And the product of these two, so let's let E1 be the span of those. And likewise for E2, it would be the span of those. E2 is related to the span of those, span thereof. Let's make this, let's in effect restrict E1 and E2 to invariant irreducible subspaces of their former selves in order to carry out this project. Now then what that means is that the dimensionality of the tensor product of E1 times E2 is just the product of the dimensions. It's 2J1 plus 1 times 2J2 plus 1. And this is equal to the dimension of what we'll call E, which is the product space. All right. Now, the basis vectors in the product space we can call gamma JM, meaning eigenstates of total J squared and total JZ with an extra index gamma if needed to resolve degeneracies. It actually turns out that if E1 and E2 are single irreducible subspaces, as I'm explaining right now, then this gamma index here is not needed and can be thrown away. So let me do that with a red marker here. We'll just X it out. And I'll show you an example of how that works out, so you'll see that it's true. But notationally, let's just use that fact to simplify the notation and just talk about Jm then is equal to the standard angular momentum basis in the product space, SAMB, standard angular momentum basis in the product space E, which is E1 tensor product E2. Now, this means that we have two bases in the tensor product space. And here's what they are. One of them is what I'll call the uncoupled basis. And this is the basis factors, is a collection of basis factors that I'll denote this way as J1, J2, M1, M2. And this by definition is just the product of J1, M1 with J2, M2. It's just the product basis from the standard Eigenminimum bases of the two constituent spaces E1 and E2. What I'll call the coupled basis is the basis Jm in the product space, which is eigenstates of J squared and Jz, where J belongs to some set, we don't know what it is yet, and the M values will run from minus J up to plus J, like so. And as I said, the multiplicity of J's turns out to be 1, so I don't need a gamma index. Anyway, there's two bases in this product space, and a basic question, a problem in quantum physics is to find the unitary transformation connecting those two bases. Now then, to follow the logic of this, I think it helps to have an example. So let's take the case where J1 is equal to 5 halves and J2 is equal to 1. It's sufficiently complicated to allow you to see how the method works. That means that 2J1 plus 1 is equal to 6 and 2J2 plus 1 is equal to 3. And so that means this is the dimension of E1 and this is the dimension of E2. And so that means the dimension of E is the product of the two, which is equal to 18. 18 basis states there in the product space. Now the way to analyze this is to make a drawing. So here I'll bring it up. Here's the drawing. We have the uncoupled basis vectors, J1, J2, M1, M1, and M2. J1 and J2 are constants. They just characterize the spaces E1 and E2, but the M1 and M2 run over their allowed ranges of magnetic quantum numbers, from minus 5 halves to plus 5 halves for M1, and from minus 1 to plus 1 for M2. Now what I've done is I've created a set of spots, and as you can see in the M1, M2 plane, maybe you can't see because there's a little yellow thing on top of it, let me pull it down. This is the M1, M2 plane, is basically magnetic quantum numbers, where I've located a spot at the location of each of the product basis states, as to say, basis vectors of the uncoupled basis. So the M1 quantum number runs from, as you can see, 1 half, 3 halves, 5 halves, minus a half, minus 3 halves, minus 5 halves. Whereas the M2 quantum number goes from minus 1, 0, and plus 1, creating altogether a rectangular array, which is 6 by 3, which gives us a total of 18 states. So this is an 18-dimensional space. All right. Now then, to construct the coupled basis states, J and M, these are going to be eigenstates of J squared and Jz. And J squared, of course, is the sum of the square of the two constituent J's squared. And the Jz is the Z component of J1Z plus J2Z. It's the Z component of the sum of the two J's. So it looks like that. So to construct the coupled basis, we need eigenstates of these two operators. Now it turns out that Jz is the easier of these two to work with. And the reason is that the basis vectors of the uncoupled basis are automatically eigenstates of Jz. Let me go to a different page and show you that that's true. So let's do this here. Get this out of the way. So this is what the statement I just made is true, because if I let Jz act on a vector of the uncoupled basis, J1, J2, M1, M2, by the definition, this is J1Z plus J2Z, acting on the product states, J1, M1, product with J2, M2. I'm omitting the tensor product sign now. And the J1Z acts on the first factor, and the J2Z acts on the second factor. And so this brings out M1 plus M2 times the product states, which I'll write J1, J2, M1, M2 like this. And what you can see is what I claimed is that each of these vectors of the uncoupled basis is an eigenvector of Jz. And the eigenvalue, if I call it M, is equal to M1 plus M2. Okay. So to go back to our diagram here, of the dots. Let me get another sheet of paper here, but useful to do this. We go back to the dotty diagram. Here it is. Let me get it so we can see it. We go back to the dotty diagram. The magnetic quantum number of the product states is the sum of the two m's. Let's draw attention to the upper right-hand corner. This is what I call the doubly stretched state, because both the M1 and M2 take on their maximum values. So one is 5/2 and one is 1. The sum of the two is 7/2. So that doubly stretched state is a state where the M value is equal to 7. It's an eigenstate of JZ, total JZ, with M equals 7/2. On the other hand, there are also states with M equals 5. So let's start a table here. Let's make a table of allowed M values. We want to find the spectrum of JZ here. That's the first problem. So the spectrum of JZ certainly includes 7/2, because we found such a state. It also includes 5/2, because both of these two states here are both M equals 5/2. I'll draw a line through them like that. This is M equals 5/2. You see a contour line of M1 plus M2 is a straight line sloping downward at 45-degree angle. So it runs through both those 2 points. They both have the same value of total M is 5/2. Likewise, these 3 points, which are in the same downward sloping line, these have an M value of 3/2. These 3 points have an M value of 1/2. These 3 have an M value of -1/2, going down by 1 unit each. These 3 have an M value of -3/2. These 2 have an M value of -5/2. And the last one, which is a doubly stretched state in the negative direction, has an M value -7/2. So we have the spectrum of JZ now. It runs from plus 7/2 down to -7/2. So let me list the values here. 7/2, 5/2, 3/2, 1/2, -1/2, -3/2, -5/2, and -7/2 for a total of 8 possible values. Now, on the other hand, these eigenstates of JZ are in general degenerate. So let's put down a degeneracy here. The doubly stretched state is not degenerate. It's the only state that has an eigenvalue of 7/2. So its degeneracy is just 1. But the M equals 5/2, there are 2 vectors that have that eigenvalue of 5/2. So this is a twofold degeneracy. Likewise, M equals 3/2, there's 3 vectors. And if you run down the table, you get 1, 2, 3, 3, 3, 3, 2, and then it goes back down 2 and 1 like this for the degeneracies. If you add all of these up, you better get 18, because that's the total number of spots, and you can check that it does. But anyway, what we see is that JZ by itself in general doesn't form a complete set, because there's degeneracies here. We need to have an extra quantum number. Well, the extra quantum number is going to be the J quantum number, which of course is the quantum number of the operator J squared, which is right down here, right there. J squared is a much more complicated operator. How are we going to get eigenstates of J squared? We want simultaneous eigenstates of J squared and JZ. How are we going to get them? Well, again, the story begins with the doubly stretched state here with M equals 7/2. I want to remind you of a theorem that I quoted in one of the first lectures. Maybe it was the very first lecture. You can find it in notes 1. It says the following, that if you have 2 observables A and B, which commute with one another, and you have a non-degenerate eigenstate of one of them, then it is automatically an eigenstate of the other one. This theorem is easy to prove, and it gets an amazing number of applications in practical quantum mechanics. This is one of them right now, because we have 2 operators, J squared and JZ, that commute with one another. And we have a non-degenerate eigenstate of JZ right there. There it is, doubly stretched state. It follows from this theorem that therefore must be an eigenstate of J squared. Now, the theorem doesn't tell us what the eigenvalue of J squared is. It just tells us that it has some eigenvalue. So we have to figure that out. What is that eigenvalue? What can that eigenvalue be? Could we have, let's call it J. There is some J. That's the quantum number. The eigenvalue is J times J plus 1. Can the quantum number J, for example, be less than 7/2? Is that possible? In other words, could we write the doubly stretched state Jm is equal, we'll put a question mark here, as to be 7/2, and then, I'm sorry, with a J value less than 7/2, let's call it, say 5, maybe it's 5/2, comma 7/2, which is the M value. We know the M value is 7/2. Is this possible? The answer is no, because this violates the rule that m has to be less than or equal to j. So this is not allowed, and so this is so j equals 7/2 doesn't work either, doesn't work. What about j greater than 7/2? Could this jm state, which is in the upper right hand corner, be equal to, let's say, to take an example, maybe it's 9/2 comma 7/2? Is that possible? Well, if that were true, if that were what that state was, we could apply a j plus operator to it, a raising operator to it, and that would raise the m value, and we get a state with 9/2 comma 9/2. In other words, we get a state in which the jz value is equal to 9/2. But there are no states with j's equals 9/2. You can see by looking at the diagram up here or the table we just went through. They run from 7/2 plus or minus 7/2 in between. So that doesn't work either. So the only conclusion can be is that j must be equal to 7/2. And therefore we conclude that this doubly stretched state here, this jm equals this, let me put it this way, the jj, the doubly stretched state, is equal to 7/2, 7/2. And therefore there's a value of j equals 7/2, which occurs in the tensor product space E1 times E2. And in fact, let me put a 1 right there because its m value is 7/2. Now, having gotten that state, jj 7/2, 7/2, we can apply lowering operators to lower the magnetic quantum number from plus 7/2 down to minus 7/2. And if we do, we get states that'll indicate by ones here going all the way down from plus 7/2 down to minus 7/2. And this gives us a total of 8 states like that. All right. Now then, let's draw attention now to the subspace of the product space where m is equal to 5/2. There are 2 states that are in there like that. So it's 2-dimensional subspace. One of them is the state we got by lowering the 7/2, 7/2. In other words, in that space, in that m equals 7/2 space, there is a vector which is 7/2, 5/2 that we got by applying j minus to the doubly stretched state. But this is a 2-dimensional space. And so there's another vector in there, which is orthogonal to this one, which has m equals 5/2. Let's call that vector x. It's characterized by the fact that jz acting on x brings out 5/2 because we're requiring it to be inside that 2-dimensional space. And we're requiring it to be orthogonal to the 7/2, 5/2. And let me just say then that with these conditions, it's a little bit of linear algebra logic, which is interesting to look at. It's a generalization of the logic that goes into that theorem that I just quoted. It shows you that the vector x must be a vector which is an eigenstate of j squared, and that the j quantum number is 5/2. In other words, x turns out to be equal to 5/2, 5/2. 5/2, 5/2. And thus this 2-dimensional space with m equals 5/2 is spanned by a pair of vectors in different ways. One of them is the uncoupled basis, 5/2, 1, 5/2, 0. And this is the J1, J2, M1, M2, you see. And the other one is 5/2, 1, 5/2, 1, and then 3/2, 3/2, 1, like so. That's what these 2 spots are right there. But another set of basis states is 7/2, 5/2. And these are the Jm quantum numbers, and 5/2, 5/2. Again, Jm quantum numbers. Okay, it's a 2-dimensional space. It's spanned in 2 different ways. In any case, this means that we've discovered that j equals 5/2 occurs in this product space, and then it has a stretch state there, 5/2, 5/2, which is right there. By applying lowering operators, we get 5/2 with the m value going from plus 5/2 down to minus 5/2, which generates a total of 6 states like this that'll indicate by ones going down like that. All right, and that gives us 6 states. All right. Now then, let's move on to the next subspace of m equals 3/2. This is a 3-dimensional space. 2 of the vectors are used up in that space by lowering states of higher j value, leaving behind only one vector that's orthogonal to the 2 that we already know. If I call that vector, let's say y, by using similar logic, one can show that that y is actually the stretch state of a j equals 3/2 irreducible subspace, like so. And then we get a 1 there, a 1 there, a 1 there, a 1 there, and a 1 there for the magnetic quantum numbers ranging from +3/2 to -3/2 for a total of 4 states like that. And once we've done this, all the spots are now used up, all the dimensionality is used up, and there isn't anything left. And this is confirmed by doing an addition of dimensionalities. 18-dimensional space, you see, is broken up into a set of 3 subspaces, which are orthogonal, mutually orthogonal, corresponding to different j values, namely 7/2, 5/2, and 3/2 of dimensions 8, 6, and 4. And 18 is equal to 8 plus 6 plus 4, so the dimensions add up. Each of these subspaces of dimension 8, 6, and 4 is an example of an invariant irreducible subspace in the product space. Although our constituent spaces, the way I set it up, the way I'm doing this problem, consists of just a single irreducible subspace, the product space here has 3 of them. Okay. Now we can summarize the results of this analysis by getting a clean sheet of paper for starters. We'll summarize the results or a clean spot on a sheet of paper. We'll summarize this in the following way. We'll write the results this way, is to say that 5/2 tensor product with 1 is equal to 3/2 direct sum 5/2 direct sum 7/2. And this corresponds to a dimension count of 6 times 3 is equal to 4 plus 6 plus 8. The direct sum, I'll remind you, is used to describe mutually orthogonal vector subspaces that combine together to create a total space, and that's what's happening here. So we say in this example that combining an angular minimum of 5/2 and an angular minimum of 1 gives rise to a total angular minimum that's either 3/2, 5/2, or 7/2. If you work this through for general rules J1 and J2, you find the tensor product of J1 times J2 is equal to a minimum value of J, which is the absolute value of J1 minus J2, and then going in integer steps up to the maximum value, which is J1 plus J2. And that's what we've got here. So this is the range of J values that occur in the tensor product space. And it turns out that each J value occurs only once. That's why we don't need a gamma index in talking about the coupled basis. We just can call it JM, and we don't need gamma JM for it. That was clear here in this example, is that each of these J values occurred once and only once. The multiplicity of the J values, one might say, is either 0 or 1. It's 1 if it occurs, meaning J lies in this range down here. And otherwise it's 0, doesn't occur. All right, so this is some of the basics of the coupling of angular momenta, which I assume you've seen probably not quite as thoroughly in your undergraduate course. Now, the net effect of this is that in this tensor product space, E is equal to E1 tensor product E2, where I'm now thinking of E1 and E2 as being single irreducible subspaces under rotations. It means that we now have 2 sets of bases in this space. I mentioned this before. We have the uncoupled basis, which is just the tensor product of the constituent basis vectors, J1, J2, M1, M2. And remember that J1 and J2 are fixed. Those just give you the dimensionalities of E1 and E2. And then you've got the coupled basis, which is JM, in which the J is not fixed, but rather runs over these values that I just listed here. And for each J value that occurs in this list, the M value goes from minus J up to plus J. If the calculation is done right, or if this decomposition or this formula I've listed here is correct, then you can do a dimension count, and the dimension count is this: is that 2J1 plus 1 times 2J2 plus 1, which is the dimensionality of the product space, must be equal to a sum in which J runs from a minimum value, which is the absolute value of J1 minus J2, up to a maximum, which is J1 plus J2. And then what you add up is 2J plus 1, which is the number of M values. So this is an identity. It's actually just an algebraic identity. And you can check it using algebra. Geometry is easier. And what it does is it gives you a confirmation or a check on the logic that underlies this decomposition of this product space into this constituent invariant irreducible subspaces. In any case, this is a description of the ranges on J and M. Okay, so we have two orthonormal bases in this space. So this means that they're connected together by the components of a unitary matrix. For example, if I take a coupled basis vector Jm, I can write this as a sum on M1 and M2, which are the labels of the uncoupled basis of the uncoupled basis vectors J1, J2, M1, M2, times expansion coefficients, which can be written this way as a scalar product of J1, J2, M1, M2, scalar product with Jm. And this is an obvious formula if you just look at it the right way, because all I've really done is I've used a resolution of the identity, which I'll underline here in red, which is based on the uncoupled basis. It's just the sum of the uncoupled basis vectors outer product, just which is equal to 1, just placed in front of the Jm. But it's also giving us Jm as a linear combination, the coupled basis vector is a linear combination of the uncoupled basis vectors with expansion coefficients. You can run this the other way. You can take J1, J2, M1, M2, and you can write this as a sum that goes from J is equal to J min, absolute value J1 minus J2, up to J max, which is J1 plus J2, and then the sum on M, which runs from minus J up to plus J, of Jm, outer product with itself, Jm, times the vector on the left-hand side, J1, J2, M1, M2. And again, this is an easy formula to remember because all we've got here is a resolution of the identity now using the coupled basis, which is equal to 1. What's underlined equals 1, just multiplying onto the basis vector of the uncoupled basis, which is on the left-hand side. So this is just expanding these basis vectors forward and backward in the two directions. These expansion coefficients which occur here in these two cases are called the Clebsch-Gordon coefficients. CLEBSCH, let me spell it right, it's Clebsch-Gordon with an A, Clebsch-Gordon. Some people quibble over this and say that Clebsch and Gordon didn't actually do these coefficients, which is true, they didn't, they did something else. And so they should be called the vector coupling coefficients, and some books do that. I think most people call them the Clebsch-Gordon coefficients, even if it's not exactly proper credit. Clebsch and Gordon were mathematicians who considered this problem of the tensor product of these spaces, and they worked out the ranges on the J values in doing it. They did this. I hope this history is I think this history is more or less correct. I'm not sure all the details I'm saying are exactly right, but they did their work roughly in the last quarter of the 19th century. So it was some decades before quantum mechanics came along. They were pure mathematicians. All right. In any case, those coefficients are called the Clebsch-Gordon coefficients. Now, the values of the Clebsch-Gordon coefficients in the way that I've defined them here depend in part on the phase conventions for the various basis states, the coupled and uncoupled basis vectors. I explained back when I was explaining raising and lowering, J plus and minus raising and lowering operators, that it's standard to choose phase conventions for the standard angular momentum basis so that the matrix elements of the raising and lowering operators are real and positive. And I also explained that it pins down all the phases for all of the states Jm except for the stretch state, which is arbitrary. Basically, you choose an arbitrary phase of the stretch state, then you apply lowering operators to fix the phases of all the others. That's the idea. However, to get the phase conventions for the Clebsch-Gordon coefficients, you also need to worry about the phase conventions for the stretch states. So there are extra phase conventions that go into making a specific conventions for the Clebsch-Gordon coefficients. And normally what's used in the physics literature is, or what are called the Condon and Shortley phase conventions, which are explained in the notes, and I won't go over them in lecture, except just to say that with those phase conventions, the Clebsch-Gordon coefficients turn out to be real. In principle, they're the components of a unitary matrix, but since they turn out to be real with the phase conventions we use, in physics on Earth, it means that there actually are the components of an orthogonal matrix. And it means, since they're real, that if you complex conjugate them, which of course amounts to reading them in the reverse order, the value doesn't change. So you can read the Clebsch-Gordon coefficient either forward or backwards, and it's the same numerical value by the standard phase conventions. Okay, so that's the definition of the Clebsch-Gordon coefficients. Now they have certain properties which I want to mention. One of them is orthonormality properties. And as far as those are concerned, let me go back to a summary page I've got here. The orthonormality equations look kind of complicated, but if you look at them the right way, you can see they're absolutely trivial. This is an example down here of an orthonormality relation connecting the Clebsch-Gordon coefficients. Here it is. It looks at the product of two Clebsch-Gordon coefficients summed, gives us Kronecker deltas. The reason it works is because if you take two basis vectors of the coupled basis and form their scalar product, you get Kronecker deltas because they're orthonormal to one another. That's just the way you set it up with eigenbases of mutual sets of commuting observables. Now, on the other hand, if I now take a resolution of the identity using the uncoupled basis and insert it right there in between these two, then I get this identity, because here's the sum right there, and here's the outer product of the basis states. So that's all this orthonormality relationship is just inserting a resolution of the identity into this scalar product. Now there's a reverse orthonormality relation also that comes from doing it the other way, taking scalar products of the uncoupled basis vectors and then inserting a resolution using the coupled basis. I haven't bothered to write it down, but it's also equally trivial if you just look at it. So these identities, if you look at them that way, you can see they're really quite simple to work with. The Clebsch-Gordon coefficients also satisfy recursion relations that are based on applying raising and lowering operators. I'm going to omit the details of that because it takes some time to write it out, and it's straightforward. But right here is an example of one of the recursion relations you can get. Basically, all I do is I take one of these formulas. Let me see if I still have it here. Let me see if I still have it here. Did I put it over there? Maybe I can't find it anymore. It was one of these formulas I claimed. Yeah, here's one of these formulas I claimed is obvious. Yeah, right. What they are obvious. And then take one of these formulas here. If I apply, for example, a raising operator to both sides, I can raise it in the JM form, and I can raise it in the uncoupled basis form, and then rearrange things. And if you do that, you get recursion relations of this form, like this. I mentioned the recursion relations because they'll come up again at least once. And also because the techniques that you probably use for calculating Clebsch-Gordon coefficients are essentially using these recursion relations. That's really what they amount to. All right. In addition to the recursion relations and the orthonormality relations, I want to mention some other properties of the Clebsch-Gordon coefficients, namely selection rules. And these are important because these end up being selection rules for many practical calculations. Let's write the Clebsch-Gordon coefficient as a scalar product of Jm with J1, J2, M1, and M2. The first selection, there's really two selection rules. The first one is that this is 0 unless the M quantum number on that side is equal to M1 plus M2 on the other side. And that's because both the vectors of the coupled and uncoupled bases are eigenstates of total Jz. In one case, on the one side, it's M, and on the other side, it's M1 plus M2. And if they aren't equal, these are orthogonal. So this is equal to 0 unless M is equal to M1 plus M2. That's a selection rule in magnetic quantum numbers. The other selection rule is the one on the J values, which I listed already. It's equal to 0 unless J belongs to the set consisting of starting with J1 minus J2 absolute value and then going in integer steps up to J1 plus J2. So these are the two selection rules in the Clebsch-Gordon coefficients. All right. That's all I want to say about the definition, basic properties, and how one calculates Clebsch-Gordon coefficients. I'm going to assume that you have calculated them before, so I'm not going to review that. But in any case, are there any questions about this so far? This is a topic you've seen before, and if you ever had any questions in the past, now's the time to ask them. If not, I want to move on to some applications of the Clebsch-Gordon coefficients. It turns out there's some interesting things you can do by combining them with the D matrices. To begin with, allow me to go back to the formula I'm looking for is right up here. It's just expanding the, actually, let's write it in this form down here. It's expanding a vector of the uncoupled basis as a linear combination of the vectors of the coupled basis with coefficients, which are Clebsch-Gordon coefficients. Let's apply a rotation operator to both sides. It's a rotation operator in the product space. U here stands for U of n hat comma theta. There's some axis and angle which is understood. If I apply this U to this uncoupled basis vector J1, J2, M1, M2, the U by definition was U1 tensor product with U2. And J1, J2, M1, M2 by definition is the tensor product of J1, M1 with J2, M2. Now, let me remind you as an aside, maybe I can find a place to do it, that in a general notation now, if you have gamma JM, a standard angular minimum basis vector in a general notation, and I apply a rotation operator to it, what I get is the sum on M prime of gamma J M prime multiplied by the D matrix, it's DJ M prime M, which is parameterized by U. It's the same U on both sides. Now this is the transformation of the basis vectors of the standard angular minimum basis. I've written down this formula, I think once before tonight, if not more than once. And part of the significance is that the whole story about irreducible subspaces is that gamma jam taken together forms a basis. So U acting on this can be expanded as a linear combination of all the gamma J and M's. But in fact, there aren't any contributions from any other gammas and J's except the ones on the left-hand side. We only get contributions from different M values. That's why this is just an M sum, M prime sum. And the expansion coefficients are the elements of the D matrices. So the U1 acting on the J1, M1 part and the U2 acting on the J2, M2 part can be expanded out just like this. And so the right-hand side begins to look like this. It becomes a sum on M1 and M2 with primes on them of J1, J2, M1, M2 prime times DJ1, M1 prime, M1 times DJ2, M2 prime, M2. Okay. But now on the right-hand side, this is equal to U applied to, I'm just going to copy the formula up above and abbreviate it somewhat. It's JM times the Clebsch-Gordon coefficient, JM, J1, J2, M1, M2. And this sum is taken over J and M. I'm abbreviating the ranges and the sums here and collapsing this double sum into a single sum, but this formula is really the same as what we have up here, except they got a U out front. And so I can let the U act on the J and M, and I can expand that out using essentially a version of this formula over here. And I get the sum on J, M, and M prime of J, M prime, DJ, M prime, M. And then the Clebsch-Gordon coefficient here is just a number in it. And so it commutes with everything. So I just copy it, JM, J1, J2, M1, M2, like so. And I'm kind of doing this in a cramped spot of this paper. I'm sorry for that. But you can see what we've got here is we've got linear combinations of the uncoupled basis vectors up here is equal to linear combinations of the coupled basis vectors where both sides have been rotated by the same rotation. And here, by the way, it's understood that these D matrices are all parameterized by the same U. So if you put them in axis and angle form, they all have the same axis and angle. I didn't write that out explicitly. Now, if I take this sum, I can pick out one term on the left-hand side by forming scalar product with a bra, J1, J2, M1, M2. I better make it like either primed or maybe even double primed if you want to be careful about indices like this. It'll pick out one of these terms. And if I do that, I end up solving for the product of the D matrices. And that's going to give you a Clebsch-Gordon coefficient over here times the D times another Clebsch-Gordon coefficient. And to save writing, I have summarized it here. And here's what you get when you do this is you get combining D matrices. is you get the product of two D matrices for J1 and J2 with arbitrary M subscripts is a sum, triple sum here, involving two Clebsch-Gordon coefficients on the right and the left and a single D matrix. So this is a formula that can be used for expanding the product of two D matrices as a linear combination of single D matrices, which turns out to be quite useful in practice. In fact, I'll make an application of it before too long. You can do this the other way as well. We could have done, the other resolution of the identity, writing the coupled basis as linear combination, uncoupled, and apply rotations. Or we can take the upper formula up here, and we can in effect invert the Clebsch-Gordon coefficients regarded as orthogonal matrices, bring them over to the other side, and solve for the DJ, which is in the middle here. In spite of all it looks complicated here, but the Clebsch-Gordon coefficients are really the components of an orthogonal matrix, and so the inverse is just the transpose. Or if you like, you run it backwards to get the matrix of the unitary conjugate, U dagger, which is the U inverse, except they're orthogonal, so the complex conjugation doesn't do anything. So it's easy to do that, and if you do, here's what you end up with: is you solve for the D as a linear combination of products of Ds, again with Clebsch-Gordon coefficients. This is I'm summarizing the result here. Now, what is this good for? Well, one thing it's good for is you can see that if I know the D's for small values of J, like J equals 1/2, for example, I can combine them together to get the D matrices for larger values of J's by using coefficients which are Clebsch-Gordon coefficients. I don't recommend this as a way of finding the D matrices for higher values of D. J, there's better ways of doing it, but at least this gives you an idea of what can be done. All right, now then allow me to allow me to do this. Let me get some clean paper here. Let's get this. I'll tear off a sheet here to get a clean paper page. This aside, I want to focus on this identity which I just derived right there. Allow me to make changes in notation. Let's change the notation here. And let's take a J1 and J2 and replace them by L1 and L2, thinking of orbital angular momentum and therefore integer angular momenta. These equations are true for any J integer or half integer, but let's specialize to the case of integers and change notation to indicate that that's what it is. Let's also take J and replace it by L. At the same time, let's take M1 and M2 and replace them by 0. They occur here and here. Let's replace them by 0 for reasons I'll explain in a minute. And then having gotten rid of them, let's take M1 prime and M2 prime and replace them by M1 and M2. And this is enough changes that it might be a good idea to write out the equation. Let's do that. So I have DL1 M1 0 times DL2 M2 0 is equal to the sum on L, M, and M prime of Clebsch-Gordon coefficient L1, L2, M1, M2, L, M prime, DL, M prime, M, and then the Clebsch-Gordon coefficient L, M, L1, L2, 0, 0. That was just change of notation was all it was, and specializing two of the magnetic quantum numbers to zeros. Now, however, because of the selection rule in the Clebsch-Gordon coefficient on the right here, you can see that the M here must be equal to 0 because we got 0 zeros over here. So the M equals 0 term is the only term that contributes, and we can get rid of the M sum in doing that and set M equals to 0 there too. Also, since we got an M prime here, let's change notation, replace M prime by M. And let's also take the complex conjugate while we're at it. So if you allow me to do this, then I'll write it out again, yet again. It's DL1 M1 0 star times DL2 M2 0 star is equal to the sum on L and M. And since I took a star, I'm going to read the whole thing backwards now. So we get L1, L2, 0, 0, scalar product with L0. That's that Clebsch-Gordon coefficient backwards. Then I have DLM0 star, copying that, except it's got a star. And now run this one backwards. I have LM scalar product with L1, L2, M1, M2. All right. So we get this identity. I'm taking this somewhere. Where am I taking it? I'm taking it to a certain place, which requires me to remind you of an identity we derived earlier. And I'm afraid I have to dig it up now. What did I do with it? Let me put it over here. Let's see here. I may have lost it. Let's see here. It'll be quicker if I just write it down again, because I remember it. Here's the identity. The identity is that YLM of theta and phi is equal to the square root of 2L plus 1 over 4 pi times the D matrix DL M0 of phi comma theta comma 0 complex conjugated. We worked out a relationship between the YLMs and the D matrices. The YLMs depend on the spherical angles theta and phi. And over here, the D matrices are parameterized by the Euler angles, which run in the order of phi, theta, and 0 for the third angle. And you have to complex conjugate it. Anyway, this was a result that we derived by rotating YLMs. And you can see then that these D stars then can be expressed in terms of YLMs. And if you do this, what you end up with is a formula that looks like this. In fact, this one, I think I do have quoted here somewhere. Let me find it. Yeah, let me get this here. I don't know why I'm having so much trouble finding the papers that I've lost here. Oh, here's one. Oh man, I lost this too. Just a minute here. Well, here I really, all right. I better just write it out. So here's what we get. Is we get YL1M1 times YL2M2, that comes from these two D's over here, is equal to the sum on L and M. There's square root factors coming from that stuff, which is the square root of 2L1 plus 1 times 2L2 plus 1 divided by 4 pi times 2L plus 1, sort of normalization factors. And then we have the Clebsch-Gordon coefficients, which I copy here, L1, L2, 0, 0, L0, like that. And then that D gets replaced by a YLM. And then I have LM, L1, L2, M1, M2. And let me box that here, because it's an interesting formula to look at, and it gives rise to a useful result. It's interesting to look at for the following reason. Let me get it so that you can see it all at once. The YLMs, of course, are forming. By the way, these three YLMs that occur here are all evaluated at the same theta and phi. I didn't write that out explicitly, but they're all evaluated at the same spherical angles. Now the YLMs form a complete set, of course, for wave functions on the sphere. So in particular, if I take the product of two YLMs, that's a function on the sphere and can be expanded as a linear combination of single YLMs. That's just what this is, except we've got explicit formulas for the expansion coefficients, and you can see they're related to Clebsch-Gordon coefficients. In fact, this is an example of what's called the Wigner-Eckhart theorem that we'll deal with later on. In any case, that's what this formula says. It's one of the things this formula says. It allows us to take products of YLMs, which occur in many applications, and replace them by linear combinations of single YLMs. Now, if I take this formula and I multiply by YLM complex conjugate and integrate over d omega, coming from, apply this to both sides of this equation, it'll pick out the one term on the right-hand side. And then you see what I get is an integral d omega of a YLM complex conjugated times a YL1M1 times a YL2M2. And that becomes equal to, on the right-hand side, the sum goes away because you picked out one term and everything else is what's left over. It's the same square root, the same Clebsch-Gordon coefficients, L1, L2, 0, 0, L0, the Clebsch-Gordon coefficient, Lm, L1, L2, M1, M2, like so. And I'll even write out the 2L1 plus 1, 2L2 plus 1, divided by 4 pi times 2L plus 1. And let me box that. And I will give this a name. I will call this the 3YLM formula. And it is very useful in applications in many areas of atomic and molecular and condensed matter physics. It allows us to carry out an integral over the product of 3 YLMs. If you have the integral of 2 YLMs, if the third factor weren't there, then it's trivial by just the orthonormality of the YLMs. But for 3 YLMs, it turns into this, and you can see the answer can be expressed in terms of Clebsch-Gordon coefficients. All right, the 3 YLM formula, as I see I'm out of time, I ran over a little bit, I'm sorry, is where we end tonight. Are there any questions about this? No questions, all right. Well, if that's the case, then we will stop screen share. And one more chance for any questions before I pause recording. Yes.
Yeah, I think I'm just thinking about that last result that you just wrote down, the
Yes.
3YLM formula.
Yes.
So you can find it for 3 different wave functions. Are these like I guess like physically, what how do you think about that? Like what kind of wave functions?
I'll be showing you some examples of that physical application of that within a couple of lectures to the emission and absorption of radiation. You'll see how it's actually used in practice.
Mm-hmm.
Let me just say at this point that products of more than 2 YLMs actually are fairly common in physical applications.
Okay. Okay. Cool.
Yeah. Okay.
Also on that formula,
Yeah.
is that formula the same as like a Slater integral that shows up in Hartree-Fock theory?
I'm not sure. I'm not sure. I'd have to see better what the Slater formula is that shows up in Hartree-Fock theory. But I can tell you that what Slater was doing in Hartree-Fock theory involves an awful lot of manipulations with identities exactly like this, including as well the products of the D matrices and things like that. These are the kind of machinery you need for doing that kind of stuff.
Okay,
If you want to talk about that in more detail, come to, I say come to office hours, but office hours are almost always used up by homework. But sometimes at the end of office hours, we have a little time to talk about other things. So come at the end of office hours and ask the question, okay?
Okay, thank you.
All right, and if we need to run over time, I can do that. All right, any other questions? All right, if not, thank you for being here tonight and your attention, and I will hopefully see some of you tomorrow.
Thank you.
All right, good night, everybody.
There.
Thanks.